Good afternoon, ladies and gentlemen. Although I'm very sad that I cannot be in beautiful Budapest, I'm very glad that the organizers have found a way to give me the opportunity to present results on a novel mechanism for electron emission from surfaces, which is characteristic for multi-quantum well structures. And the title of my talk is Secondary Electron Emission by Plasmon-induced symmetry breaking in highly oriented pyrolytic graphite. This work was done in the framework of a big European initial training network, SIMDALI2, and the partners which were involved in this collaboration are shown here in red highlighted color. So my first slide at the bottom here shows very beautiful, very low energy electron microscopy images taken at different energies, 0.8 eV, 2.7 and 5.0 eV, of graphene flakes on a copper substrate. And you can see the contrast changes dramatically when going from 0.8 to 5.0 eV. And this is caused by the fact that we see different number of layers of graphene here at different locations. And indeed, if you focus the beam on one particular spot corresponding to a certain number of graphene layers beneath the beam, and you then measure the electron reflectivity as a function of the landing energy, you see these oscillations in the resulting electron reflectivity. And these are due to so-called interlayer states. And interlayer states are formed when you put a graphene layer on top of each other, and in between the graphene layers, the electron wave functions are reflected to and fro the layers, bouncing between the layers, and that gives rise to these oscillations here. These results here by Jobst and co-workers basically are an angle-resolved equivalent of the results shown here for 2 monolayer graphene, 3 monolayer graphene, and 4 monolayer graphene. And for 2 monolayers, you get 1 interlayer state, which is showing clearly a dispersion here when going from the M point in the crystal to the gamma point and to the K point. For 3 monolayers, you have 2 interlayer states. For 4 monolayers, you have 3 interlayer states. And for graphite, you have a band of interlayer states separated by a gap. Okay, so these interlayer states can be modeled in a very simple way, in complete analogy to light optics, the case of the Fabry-Perot interferometer. This model is very simple, as I mentioned already. It contains 3 parameters: the reflectivity R, the transmissivity T, and the phase shift an electron experiences when going from one layer to the next. And then you can write down an equation for the transmissivity for n layers and the reflectivity for n layers, as is shown here. And the result of such model calculations is compared here with absolute measurements of the total electron yield measured by Alessandra Bellissimo in CERN. And you can see, depending on the phase shift that you choose, corresponding to the work function or the inner potential, you get different results, but they qualitatively reproduce these oscillations that you see in the total electron yield. So this region here corresponds to these interlayer states, which couple very well to the vacuum states, and therefore the reflectivity is very low. Okay, so these interlayer states are highly dispersive, highly transmissive, and they couple very strongly with the vacuum wave function. And whenever you use an elastic technique to see these interlayer states, for example, elastic peak electron spectroscopy, total current electron spectroscopy, or inverse photon emission, you see a clear dispersion of these interlayer states, right? So these are the interlayer states along the gamma A direction, and you see the dispersion here. However, when plasmons or energy losses come into play, no dispersion at all is observed, as you see here. Instead, you get a very, very strong resonance, completely independent of the experimental kinematics, at an energy of approximately 3.7 eV. So how is that possible? This 3.7 eV resonance, which does not show dispersion, has been a mystery in the literature for over 50 years. Elastic techniques do show dispersion, and the question therefore is, what is the influence of losses or plasmons on the secondary electron emission mechanism? And the ideal way to answer or to study that question is secondary electron energy loss coincidence spectroscopy, where one measures the intensity of correlated electron pairs. So two electrons which have interacted with each other. We do this in Vienna by using two analyzers looking at the sample, a time-of-flight analyzer shown in red here, which measures the secondary electrons, and a hemispherical analyzer which measures the energy losses. And we record the times when these two analyzers detect an event. And in this way, we get our coincidences, which consists of intensity of electron pairs correlated in time. So when we have two electrons which have interacted with each other, it means that one electron has lost a certain amount of energy and given this to the other electron. So it means we can study in this way the causal relationship between energy losses, plasmons, and secondary electrons. And this next slide here shows the result. The white curve is the singles electron spectrum. You can distinguish the elastic peak, the pi plasmon, pi plus sigma plasmon, and at the low energy side, the spectrum of secondary electrons with a very, very strong resonance at 3.7 eV. The false color in the background here represents the double differential coincidence spectrum. So each pixel corresponds to the intensity of correlated electron pairs with a certain combination of energies, E1 and E2. And at each energy along the horizontal energy scale here, this therefore represents the secondary electron spectrum for a given energy loss of the primary. Okay, what do we see? Well, first of all, we see that the pi plasmon does not lead to coincidences. This is quite amazing. The pi plus sigma plasmon, however, is creating this feature in the coincidence spectrum. Then we see these stripes at 17 eV and 3.7 eV. And at low energies, we see a peak here at 17 eV for both the energy of both electrons. And this appears to be a peak of correlated electron emission. And then at very low energies, we see the secondary electron cascade. One of the unique features of coincidence spectroscopy is that it enables us to resolve the pi plus sigma plasmon with respect to the involved interband transitions. And this is done by considering energy momentum conservation of the electron pair. So we measure the energy and the momentum of the scattered electron. The momentum we simply get from the experimental kinematics, so the angular location of our analyzer. We measure the energy and the momentum of the ejected electron. And since we know the energy and momentum of the incoming electron, we can reconstruct from this the momentum of the electron before it was emitted from the surface, so in its bound state, and the binding energy at this value of the momentum. And that's what is done here in this slide. So these data here within this red parallelogram with these equations are converted to K-space, and the result is shown in the bottom panel here, where it is overlaid on the band structure of highly oriented pyrolytic graphite along the gamma A direction that's parallel to the C-axis, parallel to our surface normal of the sample in our experiment, and the gamma K direction. And each colored dot here corresponds to a colored arrow here and indicates the electronic transitions taking place when the plasmon is decaying. And what you can recognize here is that the band gap is seen in this selective secondary electron spectrum. This is therefore the first time that the spectrum of the pi plus sigma plasmon has been resolved with respect to the involved interband transitions. We see this band gap, and we can also understand now why we do not see coincidences after decay of the pi plasmon, because simply it is energetically not possible. The pi plasmon has an energy loss of 6 eV, and you can see that the initial states leading to secondaries are coming either from the sigma band or from the pi band, and they're just too far away from the vacuum level in order to give rise to coincidences. And now, of course, if we look at these figures here, we note that these stripes in the coincidence spectra, they occur exactly at the location of these flat bands in the band structure here. So these atom-like bands. And the question then occurs how these stripes in the coincidence spectra at 3.7 and 17 eV are related to these atom-like sigma star states. In order to study that question, we have performed density functional theory calculations for the crystal as it is shown here. So the most important crystalline direction that we are concerned with is the gamma A direction, which is parallel to the C-axis in real space, which is exactly the direction of the surface normal in our experiment. So the band structure along the gamma A direction in the crystal is shown in the lower panel of this slide here as black curves. And you can identify the interlayer states here around 5 eV and another band of interlayer states at higher energies here around 17 eV. And they're intersected by states which show very little dispersion. In particular, in the low energy here, there is at 3.7 above the, approximately 4 eV above the vacuum level, there is an atom-like state without any dispersion at all. Okay, the experimental results shown in the upper panel here are the following. The green curve is the total electron yield curve measured in absolute units. And you see that in the region of these interlayer states, the reflectivity is very low, which is explained by the fact that these interlayer states couple very well to vacuum wave functions. So there, the incoming electrons can penetrate into the surface, whereas in the region of the band gap here between 5 and 15 eV approximately, the wave function cannot penetrate the surface, and you see accordingly a very strong rise in the electron reflectivity. The blue curve is the single secondary electron spectrum showing the strong resonance at approximately 3.7 eV. And the black curve is the coincidence spectrum summed over all energy losses. Okay, so if we take a perfect crystal with the perfect D6H symmetry and we simulate the transmissivity, we get the result shown in purple here. And it does not show a lot of structure. In particular, it does not show a lot of structure at this resonance of 3.7 eV. However, if we then superpose a small perturbation voltage of 0.3 eV on one of the three equivalent sp2 orbitals, we get the result shown in the lower panel here. And we see that a very strong resonant forms exactly at the energy where we observe these stripes in the coincidence spectra, or the energy where this mystery peak in the literature has been appearing over the past 50 years. So how can we explain this? Well, we have the following mechanism in our mind. A plasmon is excited and decays, and it breaks the D6H crystal symmetry. So plasmon is a coherent superposition of 5 electron hole pairs which wiggle a little bit. So certainly the electronic band structure no longer corresponds to the 1 electron solid band structure. Atom-like sigma 2 states, so these states with a high density of states, are occupied upon decay. And unfortunately, they have a vanishing group velocity, so this does not explain why electrons are leaving the surface. However, due to the symmetry breaking, they hybridize with the sigma 3 star interlayer states, which do have a finite group velocity and a good transmissivity. They couple very well to vacuum states. So the hybrid state has a high density and a finite group velocity or high transmissivity, and this gives rise to this 3.7 eV resonance, or the stripes in the coincidence spectrum. And that's the explanation for the 3 eV mystery peak, which has been in the literature for over 50 years. Okay, let's summarize this mechanism again. The Primary electron loses energy, excites a plasmon. Upon decay, this plasmon promotes an electron from the pi band to this flat atom-like band in the unoccupied band structure, which is a high density of state, but no group velocity. The plasmon also hybridizes these two states, which are involved here, the interlayer states and these atom-like states. And the hybrid states do have a finite group velocity and lead to transport of electrons out of the surface. So with this, I would like to conclude. We have resolved the pi plus sigma plasmon in graphite with respect to the involved electronic transitions. And this leads to the formation of a hybrid state as a consequence of the plasmon-induced symmetry breaking, which provides an explanation for the strong resonance observed in the secondary electron spectra for 50 years. So we have identified a new type of electrons, which is characterized not by the initial state electronic structures, such as photoelectrons or Auger electrons, but by the final state band structures in multi-quantum wells. The results provide convincing evidence that many body effects are important in secondary electron emission, which implies that the inverse lead formalism, which is often used for this purpose, is only of limited validity. And we have established a link between symmetry of a system and particle emission from surfaces. The whole story has been written up in the November issue of Physical Review Letters this year. And with this, I would like to conclude and thank you very much for your attention.